Hello, Justin.
Hello.
Oh, no. Hold on. Hello, Justin.
Hello, can you hear me?
Yes.
Okay.
How are you?
I'm good, how are you?
Let me put the volume up. Oh, I have to put. Hello?
Hi.
Yeah. Okay. Anything specific? How was the exam?
That was fine.
I think, is my volume, Justin, can you speak something?
Yeah, can you hear me now?
Yeah, and Angela, can you speak something?
Yeah, I can hear you. I'm fine.
Yeah, Justin, your volume is a little low, a little on the lower end.
Really?
Is there something you can do about it?
I can check.
Okay, I'll manage. Yeah. Try to increase it. Oops, not this. Yeah, let's see. So, how was the exam, Justin? You know, Angela is still working on.
Yeah, that was fine.
Yeah, I haven't graded it yet. I'll wait for Angela to submit, but I've given her time. So, and yeah, homework. I'll be. So there has been no homework for some time, but I intend to post it today, and we will have the normal homeworks. I think there will be 3 more homeworks. Expect 3 more homeworks within the next 3 weeks. One might be due Tuesday, next Tuesday, and then probably 2 more squeezed in the 1.5 weeks we will have. Okay. And so let me write this down. So there's homework going very slow rate, homework 7. Let me say it will be due April 21st. And there's a final exam on May 6th, but that will be take home anyway. So I'll let you know right now. Any questions you guys have? We're going to start a new topic today. We'll start working with electrodynamics, the time-dependent part of it. Okay.
Quick question, Jeff, does it still sound the same?
Now it has got better, except that there is you seem to be in a bigger room and there's a small bit of, whether you call it an echo or not, but I think I can manage. This is better than earlier.
Okay.
I'll ask you to repeat if I don't understand something.
Okay.
Yeah, this is much better. Yeah. Okay. Okay, so let's, so we want to do electrodynamics. I think this is in contrast to statics. That's what it is. And we got the equations a couple of times before. Again, Maxwell's equations are charted with E is equal to rho over epsilon naught. And we have crossed with E is equal to time derivative of the magnetic field. But let me write that on the left hand side. Zero. And we have the divergence of the magnetic field is zero. Write it as P over mu, but let me write this as, take it on to the right hand side of, let's put it this way. I typically don't write the Maxwell's equation this way. There is a mu naught times epsilon naught here, which I identified as C square. So that's your Maxwell's equation. If you were doing statics, you will set this equal to zero, this term, the derivative with respect to time of the magnetic field in the second equation, and the derivative with respect to a time for the electric field will be zero. And that actually decouples these two equations, and electrostatics becomes completely independent of magnetostatics. But now we want to do this together, and notice that these two equations do not have the sources rho and j, so they're called homogeneous equations, and in that sense these two are constraints. Right? These two do not depend on the rho and phi. Especially the third equation, that the divergence of the magnetic field is equal to zero, stays independent of whether you're doing electrostatics or electrodynamics. Whether you're doing statics or dynamics, it doesn't matter. So let's look at that immediately, because whatever you learn from that is going to remain the same. And what we learned from this is that B has to be equal to del cross A. So that is going to stay the same, right? Even when you lift the condition of statics, that's going to stay the same. If you substitute this in the second equation, then there is a del cross of some quantity that comes in. The cross of certain thing going to zero means that it has to be the gradient of some quantity, and that implies that electric field has to be equal to negative gradient of the scalar potential and negative time derivative of the vector potential. Right. So these two equations, which are homogeneous differential equations, just give you some constraints. What are the constraints? That the magnetic field has to be the curl of another vector field, and electric field has to be of this form. It can be built out of potentials. So these are constraint equations, pretty much like in classical mechanics. You say that something is constrained to move in a certain way. In this case, these are fields being constrained. These are special, out of all arbitrary fields, we are saying that it has to be satisfying the curl of some somewhere. So in that sense, this is a constraint. Once you set these to be of this form, you can substitute it in the first and the fourth equation, and that gives you an equation. And those equations are, so now these two substituted in the first place, this gives you minus del square of the electric a scalar potential, that's minus del square. And if I substitute this in there, I have minus time derivative of the divergence of the vector field has to be equal rho over epsilon naught. I'm jumping a few steps, but hopefully that's very clear. Right? Let's substitute this in there. I get that. Similarly, if I were to substitute both the electric field and the magnetic field in the equation, in the fourth equation, I get this becomes a del cross A, but then I can expand that using my vector formula, and I do get del square A, right? That's one of the terms from here. When the electric field term comes in, there's a minus and a minus, that's a plus 1 over c square d square by dt square. That's a wave equation, if you notice. Right? That shows up as a wave equation. So I still have to account for a term coming from here, and I still have to account for a term coming from there. So that's equal to plus divergence of del dotted with A, right? That's coming from here, and this is minus and a minus plus. So this is 1 over c square d phi over dt. That's all the terms together. I did it in my head, a few things. I didn't write down all the steps, but hopefully that's clear. So that's equal to mu naught J. Okay. Agreed? Hopefully that's clear. So our Maxwell's equations, after I use up the constraints, so after I use up the constraints are pretty much two sets of equation, one for phi and one for A, but they're coupled in, to a certain extent, right? There is an A showing up here, there is a phi showing up in the second equation, so they're coupled at this stage. But then so that's where we stand. So now we use what is called the Lorentz gauge. So I pointed out, I did not explore it too much earlier also, that often we can choose a gauge when we are working with potentials, not when we are working with electric field and magnetic field. Electric potentials is not completely unique. It allows a freedom, and we can use that freedom. It's like choosing an origin, right? We can always choose an origin. So similarly, when you're working with electric potentials, we have some, it's more than just choosing an origin. And here you can form the structure of the vector fields. That is a certain choice. And the choice we will use in dynamics, in contrast to statics, is that that's motivated from this part of this equation. You will choose the divergence of the vector potential plus 1 over c squared phi by dt to be equal to 0. Right? That's it. And whenever you're in this kind of scenario, one has to be very careful that that gauge is consistent with everything else what we are doing. And we will leave it this as a textbook problem and say that, yeah, this has been tested sufficiently and this is a good gauge to work with when we are working in dynamics. That's more easily said than actually done. So with that caveat, without exploring that gauge too much, I'm going to use it in our equation algebraically pretty much. And if I use that, I have two things I can do. I can replace this piece with that, and I can set that to 0. Right? There are two things I'm going to do. So again, so this is a Lorentz gauge. So I'm specifically in that particular choice. And then I have minus del square. When I replace this equation to or when I use the Lorentz gauge to replace the divergence of the vector field, I get the wave equation. So plus 1 over c square d square times the scalar potential is equal to, so let me specify that this is now, let's be very explicit, that it's a function of both position and time. That's equal to rho, which is a function of position and time, and that is epsilon naught. So it is, until now, all the problems we worked on did not have the time piece in it. That's the new part. Now we allow these charges to move around. How does that affect? And accordingly, this scalar potential will move around. In the Lorentz gauge, this piece is right away 0, and the advantage of the Lorentz gauge is that you get the same equation, exactly the same equation for both the electric and magnetic potential, which was of course the case in statics also. Right? Except that this time piece was completely not there. If you set this to 0, then you're in statics. Right? And this was mu naught times j of r of t. Right? So as of now, we were setting the condition that we are in statics. That means to say that that derivative with time was not important. It was pretty much 0, and then you solve for this equation. We called it the Green's function, and now we have a new set of equations, right? And equations at this stage. Okay, so we would like to solve these two equations. Okay. So how do you solve them? So it's equivalent to saying, let's go back and review this a little. So if it was statics, you would say this is your problem, right? So that's your rho, so let's say R, and there is no time dependence in here. What is the solution to this equation, since we worked on statics a lot? Because it's the same, going to be the same strategy. How do you proceed from this point on in statics?
Phi is Green's function here, isn't it? Something like that.
Y is what?
Phi is Green's function, right?
Yes, phi, as of now, phi is not Green's function, but you're thinking in the right line. We immediately say that, oh, this is for a general source. Let's talk about a point source. Let's say that is a point charge. Right? So you say that, okay, I want a point charge. So immediately you say that, oh, I want to say this is a Green's function, G of R, but point source can be somewhere in space. So you say that this is the position of that point charge. So instead of talking about a distribution of charges, we talk about a point charge. So that's a delta function. And you, in fact, there is an epsilon naught there, but you forget that you treat that as a differential equation, correct? And then you say that, what is the solution for G in electrostatics for this? That's equivalent to electric potential due to a point charge, which is 1 over R, right? Which is 1 over R minus R prime. And in fact, there is a 1 over 4 pi. And once you have that, you would say your electric potential due to any distribution is just adding up all these point charges. A distribution is built by adding up a lot of point charges. So you add up all of them. And that is a 4 pi epsilon. You don't forget that epsilon. So that comes here. And d cubed. So you're adding up all the point charges. Right? Rho of prime. Great. We want to do the same idea here, but now this equation has changed. We are no more in statics. We are interested in an equation del square plus 1 over c square by dt square. Right. This could be an electric potential or R of t, or it could be a vector potential, which is a function of position and time. Either one of them, right? Either one of them. Do the same thing here also. Electric vector potential also satisfies the same equation. That's equal to either rho of RT over epsilon naught or mu naught times J of space and time. And that's the equation you want to solve. And exactly like what we did here, we immediately construct a Green's function. And now the Green's function is not just in position, but both in position and time. So we'll call it the same G, R minus R prime, and T minus T prime. And again, that's because of symmetry, that translation symmetry, that it is R minus R prime. But as of now, you can also say it's R comma R prime. And this is both space and time now. Delta cube R minus R prime and delta of T minus T prime. Okay, that's the equation you want to solve. So that's a slightly different Green's function. The time piece is a new one. So what we are saying is, you're not just talking about a point charge with a disturbance at time t, right? At time t prime, a point charge moves a little. What is the electric field at t? Because of a movement at t prime, right? T prime is the time for the source and t is the observation time. So there is a difference between observation time. Today, for example, I think the best example is the light that reaches here from a star. What we see today here, which is electric and magnetic field, light is electric and magnetic field, got out of a star about many years back. Right? It depends on how far back you're looking into time. And that's what we're talking about here. T prime is the time when the source is the point charge at position R prime. If something happened at that time, whatever the motion of the charge was, how does that affect your observation at position R at time t? That's a question we're asking. Same point charge, but now we are talking about motion. Like a point charge could be moved. And that's the information of the Green function. So we want to solve that. So let's, so it's a mathematical process. So let's do that immediately. This is primarily because that is a translation symmetry. We take the Fourier transform and get rid of the time and go into the frequency space. So let's Fourier transform this Green's function. This is R minus R prime, T minus T prime. Fourier transform it. So this is minus infinity to plus infinity d omega over 2 pi. And this is minus I omega t minus t prime. Now, whatever is the Fourier transform of this Green's function, that is going to depend only on frequency and position. The time is gone now. So let's say this is the Fourier transform, R minus R prime, comma, omega. Instead of talking in terms of time, t minus t prime, we are talking in terms of frequency omega. Okay. So if I know the Fourier transform of the Green's function, I can do this integral and get the actual Green's function. That's what we'll work on. What is the equation satisfied by G? Since there is this time derivative that acts only on this piece, what will that be equal to? We have worked on this a few times, so you can substitute this in there, and the equation comes out to be square. Every derivative brings down an omega, but it brings down a minus I omega. Minus and a minus, it brings down two of them. Minus and a minus makes it a plus, but two of the imaginary quantity I make it a negative quantity there. So that's minus 1 over
The
c
screen
squared.
is kind of
This
grainy
becomes-
for me. I don't know why. Is it only for me? It's like
Tell that again.
the screen is blurred out. Your camera is kind of slightly blurry.
Slide camera is slightly blurred. Same problem, Justin?
Yeah, it's the same for me.
Same for you. Okay.
Yeah.
Let's
Like it's
move the
trying to
camera
get
and-
focused, but it's not focused. It's like that.
But it's like the whole program. I've seen Angela said the same way. Like it's the whole, all of Zoom right now seems to be doing it.
Oh, okay.
What is it? Whole Zoom. What did you say, Justin?
Like it both, I've seen both your screen blurry and Angela's screen blurry. It
Yeah,
seems
it's
to be
better
clearer
now.
though. Yeah.
It's clearer now.
Can we manage?
Yeah, this is okay now.
Proceed. Okay. Okay. So basically, time derivative brings down a minus I omega. Square of it makes it omega square over c square. Right? This becomes, that's the difference. And now it is just r minus r prime. And now it's a frequency. So notice the frequency part, the time derivative is gone. It is just a just an algebraic relation now, and the time part has gone. Again, I've used what we have done a few times before. So let me know if there is a difficulty in understanding how I went from this step to this step using this. Okay. So if you don't stop me, I'll proceed. And now what we are saying here again, we are talking about a point charge placed at r prime. This time we are not talking in terms of time, we are talking in terms of frequency, but frequency is fixed for a particular frequency, what happens. So what happens when you keep a point charge at r prime and observe it at point r? That is a whole space, in the whole space there is just one point charge. And I can keep it wherever I want to, but since there is only one point charge, why not keep it at the origin? Okay, there should be no difference there because there is just one point charge and there is an observer there, of course, but it's going to depend on r minus r prime anyway. So let's choose this r prime to be 0. So there's a significant simplification there. So this is negative radian square minus omega square over c square. And this is g tilde r 1 omega, and this becomes tilde cube of r. Right, so this is, I've chosen my source to be at the origin. Right, that's a choice, I think. And if the point source is at the origin, like imagine a whole universe, at the origin there is a point charge sitting, there is nothing else, and you are making an observation somewhere else in space. And we're talking in frequency, not in terms of time, so it is not moving in that sense, right? There is only different frequency of radiation that is happening. So it doesn't matter whether you're on the right side of the charge or on the left side of the charge. There is no right and left in a universe where there is only point charge. Is that clear? So there is no orientation. Like in whatever direction you look at, wherever the observer is, it's going to see the same thing. There is a point charge at distance r away. There is no orientation in such a space. And for that reason, this vector r cannot depend on the orientation. It can depend only on the magnitude. Okay, that's a symmetry argument we are invoking. So there is no orientation dependence. So even though this is gradient Laplacian, which has a angular derivative, it's not going to act on it because this will have only a magnitude dependence. So that's a symmetry, spherical symmetry we are invoking. And then this becomes 1 over r squared because it depends only on the magnitude. In principle, this should be a partial derivative, and partial derivative with angular coordinates. What we are saying, all that is 0, and so that's minus omega squared over c squared. And this is g tilde of r alone of omega. And on the right hand side, there is a delta function. So that's 3 delta functions in there. So this is equal to delta of r and distance, there is a theta and there is a phi over r squared. Right, that's the delta function in spherical coordinates. On the right hand side, still there is angle theta and angle phi, because that's the observation point is decided by the angle theta and angle phi. But we don't want that. We want to get rid of that. So we just integrate over with respect to angle theta and phi. So integrate over with angle theta and phi, and what we get is on the right hand side, that will become all the theta and phi will go away. But when you're integrating with angle, the solid angle is 4 pi, so that gives you 4 pi on the left hand side. So our equation simplifies. There is now only only the magnitude r that comes into picture. So it's a one-dimensional problem now. Is equal to delta r over r squared. Remember, this is unlike a one-dimensional problem. In one-dimensional problem, for example, if it was x, it goes from minus infinity to plus infinity. Here, r goes from 0 to infinity. So it's slightly different from the Green's function we have seen before, where if it was an x, that goes from minus infinity to plus infinity. Nevertheless, we can find the boundary conditions on this. Let's integrate this with respect to our boundary conditions. We call it continuity conditions usually. Let's integrate this about the center. For remember, r here has to be less than infinity and greater than or equal to 0. So usually to yes.
Can I interrupt you for just a second for something that's confusing me? For the left-hand side for del squared, we changed it to the 1 over r squared ddr r squared ddr there. Where does that come from? Can you explain that?
This is from the, okay, let me use the other board to clarify maybe. So this is the Laplacian and spherical coordinates. So this is 1 over r squared partial derivative. So my blocking it, so this is r squared d by dr plus 1 by r squared 1 by sine theta d by d theta plus that's 1 over r squared is in the denominator. So that's the Laplacian in spherical polar coordinates. Okay, But now we are saying that it is acting on a Green's function, which in general can have r, theta, and phi. Correct? But we are saying that there is no angular dependence. The electric potential due to a point charge does not depend on which direction you look at. For a particular frequency, not in time, because if you're in time, then it is moving. And then we cannot be sure about that, then it depends on the motion. But if you convert the information about the time into frequency, for every frequency, it's the same position, right? It doesn't care for that. And then there is no angular dependence. So there is no theta, there is no phi, there is no angular dependence on this. So all these derivatives go to zero. Like whenever they act on the Green's function, that does not contribute. So if in that approximation, this becomes 1 over r square d by dr, r square d by dr. But now there is only one coordinate, right? We are talking about a single coordinate. Then that partial derivative is a total derivative, and that's what I used there. Does that help?
Yeah, thank you very much.
Yeah, okay. So if I proceed then, let me go back to here. So that's the equation you get. So again, you have a total Green's function in space r minus r prime and t minus t prime. We Fourier transform this, time becomes frequency. That's your equation for the frequency. Then we said that there is no angular dependence in the Green's function. Then we have this particular equation for the Green's function. But now we want to find out continuity conditions for this. So let's integrate this equation. Remember, r is going from 0 to infinity. So imagine that there is a point charge sitting at the origin and you integrate on a sphere around that. The angular coordinates already has been integrated out. So you're basically integrating from 0 or in the limit 0 tending to 0. So you're integrating here from, integrate from left to right. So remember, maybe I should go back here, right? Let me remind you a little what we're doing. So remember, d cube r in spherical polar coordinates is r square dr. Then there is sine theta, d theta, and then d phi. Right. What I have done is that I've already integrated this. That gave me my 4 pi. So I still have this r square remaining. So whenever, if I were to integrate on a sphere, I have to give this weightage of r square. If I'm integrating over a small sphere around the origin, then there is a factor of r square that shows up. And that's exactly what I want to do. So I'm integrating over that origin. So r square cancels out. And I'll be doing minus 0 to, let's say, delta, right, or epsilon. So epsilon, which tends to 0. I'm integrating r from 0. Oh, I don't want to say epsilon because epsilon will be epsilon naught, right? Let's say delta. 0 to delta, which you want to tend to 0. So a small sphere enclosing the origin. So that's r square dr 1 over r square d by dr r square d by dr of g. Children. Okay. There is a second term where there is a Green's function integrated over the origin, but you want a delta function on the right hand side. So that has to be equal to 0. If it was not 0, then if there was a discontinuity in it, the integral over that will not give you a delta function. It will act on that discontinuity to give you something more than a bigger discontinuity than a delta function. So that has to be equal to 0. And that's equal to, same idea on the right hand side. You integrate from 0 to epsilon, delta tending to 0. r square dr and delta function of r over r square. And the good part is that r square cancels out. That was the idea. And this gives you 1 because you're capturing the delta function at the origin. Delta function actually means that there is a point charge there. It has to capture that because this is a small sphere enclosing that. So this will be equal to 1.
The delta in the limits is radius, right?
Yes, that's the radius of the sphere. That's correct.
Delta is the radius of the sphere. Okay, it's a small sphere. That's what we're saying.
A very tiny sphere, and you're taking that's the limit that tends to 0, but that's not being set to 0. And actually, while you're saying that, I realized that I integrated over angles here, right? Theta and phi. And I said that earlier that when I integrate over theta and phi, I get a 4 pi, right? Sine theta d phi is 4 pi. On the right hand side, it's a delta function that just gives you 1. But on the left hand side, I should get a 4 pi. And that gives me a 4 pi here. I forgot to write that. I said it. But I will get a 4 pi. That gives me, it's actually on the left hand side. Because there are no angular coordinates, it will give me a 4 pi. But then I put it on the bottom there. Okay, so that's 4 pi. And that 4 pi will show up here. So this will be 4 pi there. And this will be 1 over 4 pi. The r square here cancels on the left hand side also. On the left hand side, this is a total derivative. Typically, that's what happens with Green's functions. We have done Green's functions before. And this has to get contribution from at the delta tends to 0 limit. So the way you would say this is that limit, so d by dr, so limit r tends to 0 of r square times d by dr g tilde, right? Because at the lower limit, anyway, it is 0, and on the upper limit, that's what r square is, and this is equal to minus 1 over 4 pi. I moved it to the right. So the condition is whatever our Green's function is, in the limit r tends to 0, it has to satisfy this. So the derivative of the Green's function has to be equal to minus 1 by 4 pi over 1 over r square. This is not a finite quantity, and the limit r tends to 0, it will blow up. Right? So what we are talking about is about the power law relation of this Green's function. So it is not going to be finite as you tend to 0, but we can at least know what is the power. Whatever it is, derivative of that should be 1 over r square. That's what you're saying. So this Green's function should have a 1 over r dependence. That's what we're talking about, right? Because only then, if this has a 1 over r, then derivative of that will have 1 over r square. 1 over r square times r square will give you a factor of constant, which is minus 1 over 4 pi. So that's the point here. That's the information in this relation, which we can conclude from the equation itself. Right? Any questions at this stage? Okay, so this suggests that there is a 1 over r, but we can actually invoke that right away and not really an assumption, but we can separate that out. So since we know that there is a 1 over r situation there, so we are looking for r omega, right? That's our solution. And we have just now argued that in the limit r tends to 0, there must be a 1 over r form for the solution. So let's say that this is equal to 1 over r. But that cannot be correct, right? That's the static situation. So whatever extra is there, we will call it g tilde of r omega. So I've not done anything. It's just that I've taken out an explicit r in it. So this is an unknown. So I have written it in terms of another unknown, but I've given it in some structure. I've given it some structure in there. So that's 1 over R. What's our Green's function equation then? Let's go back and see what's our Green's function. How does our Green's function equation look like? So let me take derivative with respect to R of G tilde. So, so that's equal to, now I can hit this R. All right, so this is minus 1 over R squared. This is G tilde over R squared. Or I can hit my G tilde itself, that's plus 1 over R. That's my first derivative. But my differential equation has an R square in it, so let me do R square d by dr of G tilde. That's equal to minus tilde plus R times this, according to our relation in the limit R tends to 0 is equal to minus 1 over 4 pi. But let's not worry about that at this stage. Let's do one more derivative. When I take one more derivative, this is minus G tilde over dr. Here I can hit on both ones. So if I hit the first R, I get G tilde over dr, or I can hit the other one. So it's plus R square, no, R times second derivative. But this cancels out. Right, so 1 over R squared, so which is what our equation has, 1 over R squared d by dr R squared. Our differential equation is in terms of this operation. That's actually equal to just 1 over R and second derivative R squared and G tilde. That's what it is. Our original differential equation was minus 1 over R squared d by dr R squared d by dr, no, minus, right? Minus minus omega squared over c squared is equal to, what was our relation? So just 4 pi R squared. So this delta R over 4 pi R squared. But we have just now shown that this piece acting on G tilde is simply 1 over R times that. So it is minus 1 over R times second derivative. We're still in the, yeah, in the root. That's R squared times small r G tilde. And the second piece is minus omega square over c square 1 over R G tilde. And that's equal to 4 pi R square. One of the R cancels out in the equation, and our relation, our differential equation now becomes minus with sort of series of substitutions. And this is delta of R over 4 pi R. Let me check a simple thing here. Yeah, that's it. Remember, R is always greater than 0. That's only one region. Typically, we have a Green's function which is there on the left-hand side and on the right-hand side, but that's not the case here. If R was not equal to 0, so let's say R is not equal to 0. So there are two possibilities. At R is equal to 0, something happens which is right at the origin, but then there is nothing else on the other side of the origin, right? There's only one side to the origin that R is greater than 0. There is no R less than 0. So if R is not equal to 0, that's a simple differential equation. This is plus, so this is second derivative of R squared G tilde, right? That's equal to minus omega squared over C squared times G tilde. Only if R is not equal to 0. But we have to be careful about R equal to 0. That has a boundary condition there or a continuity condition there. In the limit R tends to 0, we know how that behaves, right? It has to have that 1 over R square or 1 over R form. This has an easy solution, right? What is the solution for this?
Exponential minus.
Exponential, right? It is a sine and cosine, so exponential periodic solutions. So we now have the solution of R omega to be equal to, it could be plus or minus, right? So, yeah, and let's me just, yeah, so it can be A, some constant A times e raised to I omega over C times R. Correct? That's what depends on. Plus, that could be B e raised to minus I omega C over R. Just to, since A and B are unknowns, it doesn't matter what I do, just for foreseeing some constant, let me put a 4 pi there. So that's the differential equation if R was not equal to 0. Right? But it also has to satisfy when R is equal to 0, there is a limiting condition we have, and that is that which is right on the left hand side here. If you can see down here, the limit R tends to 0, the derivative of G has to be equal to minus 4 pi. So we just have to satisfy that. So let's do that. Any questions at this stage? So we did a series of substitutions. We started with a total Green's function, did a Fourier transform, worked in the frequency space, used spherical symmetry, made a substitution of 1 over R times G tilde, and finally we have a solution for small g. Once we have small g, we can get capital G. Once you have capital G, we can Fourier transform and get the complete Green's function. So we have to go back, reverse all the steps from this point on. But before that, let's find what is the form at R equal to 0. Okay, so no questions, I assume. So our solution for small g, so remember capital G of R omega is 1 over R times small g. But we now have a small g, substitute that in here. So we have A over 4 pi times R times exponential of I omega C over R plus B over 4 pi R e raised to minus I omega C over R. That's our Green's function, but with arbitrary A and B. But the arbitrariness in A and B will be gone if we use the condition that at r equal to 0, it has a very specific limit. And what is that limit? That is given in terms of derivative, right? So let's do the derivative with respect to r. Derivative with respect to r of this Fourier transformed Green's function. It can hit here r, this r, or that r. So this is minus a over 4 pi r square times exponential of I omega c over times r. Let me hit the other one first. So this is b over 4 pi r square exponential of minus I omega c over r. And I can also hit on the in the argument of the exponential. When I hit the argument of the exponential, it brings down an I omega over c. So that is a plus I omega over c times a over 4 pi r times e raised to I times r, and bring down the same thing from there, which makes it a minus I omega over c times b over 4 pi r times exponential I minus I omega c. And our condition is that our limit delta or limit r tends to 0, right? That was what it was. Like limit r tends to 0 of r square times d by dr g tilde is equal to minus 1 over 4 pi. Right, that's our limiting condition. Let me substitute an r square there. And at the same time, let me substitute r equal to 0 wherever I can. If it's in the denominator, I should be careful. But if it's in the numerator or in the argument of exponential, I can set it to 0. So this condition in this equation sets, since I'm multiplying by r square, that r square is gone. So that's minus a over 4 pi. That's going to 1. This is minus b over 4 pi. The next two terms, I'm multiplying by an r square and then taking the limit r tends to 0. Exponentials are 1. These two will go to 0. So that's equal to minus 1 over 4 pi. That's the condition I get by setting r tends to 0 in this expression. If that is the case, minus sign goes away, 4 pi goes away. So that implies that whatever these arbitrary constants were, you can set whatever you want, but a plus b has to be equal to 1. So your solution for Green's function is this, but with this restriction that a plus b has to be equal to 1. Okay. With that in mind, let's go back. So that's our Green's function now. And now, since remember we set our r prime to be at the origin, at this point I can release that and get my complete irrespective of the choice. I can say this is r minus r prime now and omega. The understanding is that it depends only on the magnitude of the distance between the source and the observation point. So our solution will be a over 4 pi times exponential of I omega over c. Instead of writing r, I simply write magnitude of r minus r prime. So that's how I bring back my choice of origin. And this was r minus r prime. It's like saying typically we talk about what's the electric potential due to a point charge is 1 over r, but if you want to specify with respect to the position of the charge, then you say it's r minus r prime. So everywhere there's a magnitude, you'll replace it with that. But there is another factor b here. With the feature that this is actually okay. If omega was equal to 0, that leads to, if omega was equal to 0 again, let me so if omega was equal to 0, we are in frequency space, remember? If omega was equal to 0, this seems to have the solution a plus b over 4 pi times r minus r prime. But a plus b is 1, so that's 1 over 4 pi times 1 over r minus r prime. That's our static solution, which makes sense because static has to do with time going from minus infinity to plus infinity without any change, right? When you have nothing happening from minus infinity to plus infinity, that's pretty much static. But in the Fourier transform, a large time means a small frequency. So omega equal to 0 is the static limit. If you want to ask what does statics mean in the frequency space, that's 0 frequency. 0 frequency means time period is very large. So if something is happening so slowly that it's practically statics, right? So again, what does statics mean in the frequency space? Basically, you're talking about 0 frequency or time period being very, very large, infinite time period that it never achieves any motion at all. So that's your Green's function in the Fourier space. In the frequency space, now we just have to do the integral to get it in the time space. Any questions at this stage? Okay, so let's proceed. So almost there, one more step, Fourier transform, and we get the solution. But we still have this a plus b equal to 1, right? We have to set that. We hopefully can remove that arbitrariness. It seems like there is an arbitrariness in one of the coefficients. So our Green's function in the Fourier space is 1 over, no, it's a double, right? Or still, oh, we should more space. So G tilde R is equal to a over 4 pi exponential of I omega over C, just copying back, plus B over 4 pi exponential of minus I omega over C, R minus R prime over R minus R prime. With the idea that A plus B has to be equal to 1. That's your solution in the frequency space. If we want the solution in the time space, this is our actual Green's function which we are interested in, which is what we will use in the rest of the semester. The complete Green's function in electrodynamics is integrate over all frequency. E raised to minus I omega t minus t prime. Integrate over all the frequencies going from minus infinity to plus infinity, all possible frequencies, and G tilde, the Fourier transform Green's function. So if I integrate whatever is on the top, I'll get the complete Green's function. We don't have to worry about the R dependence because this integral is on frequency. So the only quantity that depends on the frequency is the exponential, and exponential functions are easy to integrate. So let's see how this looks like. So let me write down whatever is frequency independent outside, right? So it is A over 4 pi, 1 over r minus r prime. That's not frequency dependent. Rest everything is. So this is minus infinity to plus infinity e omega over 2 pi. And there is an exponential factor here, and inside there is another exponential factor. So let me write that down together. So this is e raised to minus I omega, and then there is t minus t prime. And if I were to pull down a minus, there is minus of I omega I have taken out. So it is r minus r prime over c. That's the first piece. And there is a second piece there, plus e over 4 pi e omega over 2 pi. First piece is the same exponential, t minus t prime. But the second piece has a plus there. Right? When I pull out a minus omega, it's a plus r minus r prime over c. Okay. What is this integral of exponential function? What is the integral of an exponential?
Delta function.
Good, very good. So it's integral of an exponential is exponential itself, but this is going from minus infinity to plus infinity, right? So that's a delta function, right? Very good, right? Integral of a exponential is a delta function. So that's a delta function. That's another delta function whose argument is given by the square bracket quantities. So very good. So we have the solution. Will this fit in? Yes. Here. This is equal to a over 4 pi delta function whose argument is t minus t prime minus of r magnitude of the distance between observation point and source point, and divided by r minus r prime. Remember, if that numerator was not there, it is statics, right? And then there is one more piece, b. Not off the, yeah, I'm still inside the board space. Only difference here is the sign in front of that magnitude of r minus r prime. That's your Green's function. It is the old Green's function for the static case, but now with a delta function which says that, so what does the delta function mean? Remember, t prime is what happens to the source at a certain time. T is your observation time. And what the delta function is saying is that what you see at your observation point is decided by how far your observation point and the source point is, and light has to travel that. Distance over time is speed, right? That's that relation. Speed is distance over time. So your observation time, if it is farther than how far light can reach, there's no way that's zero. This will contribute only if speed of light can reach there within the amount of time it has. Only when this is satisfied, distance over the time is equal to the speed of light, that is an observation. Otherwise, it's zero. So if you're before that, if you're after that, either way, you do not get any information. It's only when the light reaches you, that is some information. So this is, let me write that, let me point that out. But there are two delta functions, right? That's something you should worry about. So let's see the observation point here, t. So the first one is when t is equal. So when does the first delta function contribute? That's what I'm asking. So t is equal to t prime plus right. So how do you interpret this? At t prime, something happens to the source. That is a disturbance at the source. This is the time light takes to travel the distance between the source and the observation point. And this is that particular time. That's good. That is a possibility. Right? That is at t prime, and you're adding some time to that. Let's see the next term. In the next term, you have t is equal to t prime minus of r minus r prime over c. This seems to suggest that you have to subtract the time. Here t is greater than t prime. In this case, t is less than t prime. Is that clear? Like that you're adding a positive quantity here, so t is greater than t prime. Here you're subtracting a quantity here, t is less than t prime. That's not possible, right? If something happens, the effect is not going to, the observation cannot happen before that time. So this is causal. This is not causal. Is that clear, the argument? There are two solutions in electrodynamics. Those are these two pieces here. But now, at this stage, we will say that physics, as we know it, is always causal. Okay? We don't know anything that is not causal. If you want to do such physics, you got to keep the second term. Maybe there is some information in there. But in this course, we are going to keep that to 0. We will say that there is no, we will not encounter any places where causality is valid. So we are going to set this equal to 0 by choosing B to be 0. There's a choose B equal to 0 by invoking causality, or by requiring causality. That's very nice, because you would like to study, oh, like, is there any physics possible where causality is not obeyed? Then you want to come back to this point and release this condition B and see if there is any way you can measure this B. Right? Then you have a prediction. But we are right from the beginning at this stage. Like, so everything we do in the rest of the semester is going to be with the assumption that we are not invoking any acausal relation. With that, we set this whole term equal to 0. If that is 0, then A is 1, right? A plus B has to be 1, remember, right? So there was this condition here that A plus B has to be equal to 1. If you choose B equal to 0 because you don't want causality to be violated, you want causal behavior in physics, then A has to be equal to 1. So our Green's function then becomes, right? So our Green's function then becomes, let me write it, let me go to the fresh space. So our Green's function is T of R minus R prime, T minus T prime. Everything in here, 1 over 4 pi delta function of T minus T prime minus R prime over C. There's only one piece, A is equal to 1 and R minus R prime. That's it. That's your total Lagrange function. Okay. If you know the Lagrange function, then we know the potentials. Right? Phi of RT is equal to, remember, we said this is 1 over epsilon naught times d cube R prime dt prime, and then the Green's function R minus R prime T minus T prime times rho of R prime T prime. This is like saying, if you know the solution due to a point charge, I integrate over all point charges. But now I know the solution of a point charge at a certain time, so I integrate over all time. And it is guaranteed that this will be causal. When I'm integrating over all time, I have to make sure that I don't account for any future events without accounting for past affecting that. And that is taken care of by this delta function. This delta function will make sure that I will never invoke something in the future without past affecting the future. So that's what it is. And that's equal to 1 over 4 pi epsilon naught e cube R prime, e cube T prime. All these are going from minus infinity to plus infinity. And there is this delta function T minus T prime, which can be easily worked out, right? This is delta function. That's an easy integral to do. And we'll work on that next time. R minus R prime and the charge. This is for arbitrary charge distribution, remember. Arbitrary charge distribution. Same thing for the vector potential. It is mu naught over 4 pi d cube R prime, d cube T prime, same T minus T prime times J of R prime, T prime. Okay. So notice we are in electrodynamics, all time, all the variations in time is allowed, and we can get the potential and the vector field, electric potential for any arbitrary charge distribution moving with time and any arbitrary current density moving in time. And we'll begin from here and then work on specific case. So this is the basic construct here. Any questions? Maybe I can write one more step. Once I have the potentials, remember magnetic field is B cross of that vector potential. Derivatives are always easier to work out. It might be labor intensive, but always possible to do it, right? Integrals are harder to work out, but derivatives are easier. So once you have the potentials, you simply take the derivatives and get the fields, and fields is what we are interested in. And we will do specific cases in the rest of the semester, which is only about 2 or 3 weeks. Ideally, we should have had about 4 or 6 weeks for this, but partly because I delayed at various points and because we lost some time here and there, we have only 2.5 weeks remaining. Okay. Questions, comments? Did I hurry today? Did you feel like I hurried today?
No,
The pace? Pace was okay?
that's fine.
Okay. Good. Okay, good. Thank you.
Thank you.
Right.
Take care.
Yes,
Oh yeah, about the class you said Wednesday, right? You wanted to have a class tomorrow.
Oh yes, I wanted to tell. Yeah, I said Wednesday we could have a class last time, but since Anshula is not yet recovered, do you want to change that to next Wednesday? I just want one Wednesday.
I think Justin has some commitments on Wednesday. I don't know when he's free.
Oh, okay.
Works for you,
What
Justin?
about Friday?
Yeah, Friday works again, as long as it's like not before 4 o'clock, then Friday's fine.
Friday
Yeah,
4
Friday
is
4.
fine with me as well.
Yeah, so let's do Friday. So this Friday, then it is possible, right?
Yeah, it's
Hopefully,
fine.
Anshula
Yeah,
will be now recovered completely by Friday.
yeah.
Okay. Do remind, yeah, we will meet on Thursday, right? Do remind me that there is a class on Friday. I might just forget because it's just routine.
Okay.
If you don't mind, if you can remind me, that will be very helpful.
Yep.
Okay. I think that way we might be able to make it a little bit, not everything that we have lost, but I will have some breathing space. Okay, thank you.
Okay.
Good.
Thank you, everybody.
Yeah. Bye. Oh, yeah, I'm not on the screen, sorry.